So let's continue talking about fluid pressure here today. And actually, I want to show some pictures. Actually, I think we have some people from California here. It is a picture of the three Shastas, which is in the northern part of California, a couple of hours outside of Sacramento. The three Shastas is Mount Shasta in the background, which is a volcano. You have Lake Shasta right there, which was formed when they built the dam in the 1940s, Shasta Dam right there. When I was at the Bureau of Reclamation, I had an opportunity to work on a feasibility study to look into raising the dam by 20 feet. The capacity of Lake Shasta is 4.5 million acre feet. Our biggest one in Colorado is like 100,000 acre feet. Our biggest reservoir, like Blue Mesa Reservoir, is like 100,000 acre feet. So this is a lot of water, 4.5 million acre feet. This is during a spill event over the spillway. They also have some penstocks down here in the left corner, these pipes coming out of the dam. Those are feeding a hydroelectric plant. A picture of the dam under construction from the Congressional Archives. Look at all the statics that's going on here. We got pulleys right here. We've got cables subject to discrete loads. We have these truss structures over here for the towers. And then we're going to talk about fluid pressure here today. Specifically, what we're going to look at is the gates on the top of the dam. The existing, they're controlled by three 110-foot wide drum gates, each weighing 500 tons. The maximum overflow rate, 267,000 cubic feet per second. That is a lot of water. For anybody that's seen Clear Creek during peak runoff, the highest I've ever seen it is about 1,600 to 1,700 cubic feet per second. And that is ripping through there. Like, there is no way you're going to swim across that. That is a lot. 1,500 cubic feet per second is a lot of water. We're talking about 267,000 cubic feet per second. This is for the maximum flood loading that could occur at Shasta Dam. It's in the Sierra Nevadas, and that worst case flooding is a rain on snow event. I've always wanted to see a rain on snow event. It's where in the Sierras, they get dumped on snow in one day. Maybe they get 5 or 6 feet of snow, and then it warms up, and the next day they get a big rainstorm, and that rain falls on the snow, it melts the snow, and now you get all this water rushing down rushing down into the reservoir. And so they need to be able to release it so it doesn't overtop the dam there. So that's why they have that spillway to design for that 267,000. And then I just had to show this picture because this chief engineer, Frank Crow was also the chief engineer on Hoover Dam, have to declared, look at that Shasta Dam. That dam will stand there forever, holding back the river, and that powerhouse will keep right on turning out juice until somebody discovers how to make power out of sunlight. And that was said around 1945. Well, we have figured out how to make power out of sunlight, right? It's like a big part of our renewable energy system here. But hydroelectric is still an important part because you can turn it on and off really quickly, although it's really small compared to how much we can generate with the other sources of renewable energy. Also think about, 1945, this was a huge project, a big new piece of technology. Where are we going to be at in 10 or 20 years? What is going to be our big thing moving forward? Okay, so let's talk a little bit about the dam raise here. And this is a model of a cross section of the dam. And the original crest was about right here. And so we're going to raise it by 20 feet up to elevation 1,096. To give you an idea of the height of the dam, the bottom of the dam was at elevation 586. So we're 510 feet tall. This is a program that calculates all the hydrostatic fluid pressure that's acting on the dam. This part right here, you can't see them because there's so many arrows, but there's all these arrows that are acting normal to the surface. Remember that our pressure is basically equal to gamma times H. And so we see a linear increase in pressure. So our first thing that we needed to do with fluid pressure is just to be able to figure out the pressure at any point. And then the second thing with fluid pressure, kind of recapping where we left off before the exam, is that it's always normal to a surface. So there's this baffle on the upstream face of Shasta Dam. Well, the pressure changes direction right there, and it's still increasing. We can still calculate our pressure is still going to be equal to gamma times whatever height of water we have right there. And so we can still calculate the pressure, it's just that it changes direction. Actually, the sloping surfaces is what we're going to focus on in today's lecture. And specifically the gates, because they had these existing drum gates. And when we raised, or when we were looking at raising the dam, I don't think it's been raised yet. This was back in 2007 or something like that. When we were looking at raising the dam, they had these existing drum gates and we needed to replace those. But look at just in general, the angle, this is where the water would sit. The water would sit on this side over here. In general, look at the angle of that gate. Well, our proposed gates had more of an angle like this, like almost straight up and down. Well, that created some huge issues during earthquakes. This is in a very seismic region of California. And actually what was going to happen during an earthquake is the gates weren't going to fail, but the whole concrete is going to rip off of the top of the dam, and then they wouldn't be able to control the spillway section of that. So what we're talking about here is it would rip through this concrete right there and rip through all of this concrete right there. And right there, the gates would go flying down into the canyon below, and we'd have this huge disaster. So that's what we're going to focus on today, is the sloping and curving surfaces that are subject to our hydrostatic fluid pressure. So that's our only learning objective for today, is to look at those two. And we really already have all of the concepts here for fluid pressure. We did a little bit of a recap when we were talking about Shasta Dam there. I've actually never got to visit Shasta Dam. It couldn't justify for me to go out there and visit when I was working on that project. But we'll take a little field trip today and we'll do a little bit of work on Shasta Dam. And so our new gates kind of had a unique support system. We're going to change it up to look a little bit more like statics. And we're also going to do a scaled model just to make the numbers a little bit better. So we're going to be given one of these gates here. And so the gate is going to look like this, and then it sits on the crest of the dam, and it'll sit right on the spot on the crest of the dam here where the slope is equal to 0. So basically it's a flat spot right there. We can call this point up here point A, and we'll call this point right here point B, and that's just going to be a smooth contact is all we're going to call it right there. The gates at Shasta were supported a little bit differently, but it'll give us the general idea of what we ended up doing. And so those radial gates that I showed you, where the face was basically vertical and it was going to cause the concrete at the top to fail and then the gates to fail during an earthquake. Well, one of the people I was working with that had been there for like 30 years was like, why don't we change the angle of those gates? Like, we're having these issues with the with the earthquakes failing these gates. Well, it's because the gates are basically straight up and down, and all our fluid pressure is acting perpendicular to those gates. Well, if we change the angle, that means we change the angle of our fluid pressure, and we're actually going to get pressure that's going down into the dam. Concrete is really good in compression, and so that pressure going down into the dam is actually going to stabilize the dam. And so we were shooting for an angle of 45 degrees. Because of the geometry at the top of the dam there, we got actually closer to 42 or 43, if I remember correctly. Let's just put, for our example, let's make this 40 degrees. So we're going to have a 40-degree angle right there. We'll put our water all the way up to the top here of that surface right there. And then we have some other dimensions on here, like the length of the gate here from A to B is equal to 3.11 feet. So it was more like 30 feet, but we're going to go with 3.11. The distance between here and here was equal to 2.38 feet. And this all is really coming out of the fact that our gates were about 20 feet tall. We'll make them 2 feet tall just to make our numbers a little bit more manageable to deal with. So there's what we're given. And we are asked to find, for this problem here, the normal force at B if the gate width is equal to 3 feet. It was more like 30 feet. In reality, we'll make it 3 feet here. So we kind of have a 1/10 scaled model, or something close to that 1/10 there. So let's look at our solution for this problem. And the first thing that we want to do is an FBD of gate A to B, because that's going to have all of our reaction forces and all of our pressure, our fluid pressure as well. So let's draw our A to B here. So there's our A to B. We'll draw it a little bit bigger. And then at A, this is a pin. So this is going to be an AX and an AY. And then down here, it's just a smooth contact. And we're assuming it's right there at the top of the crest. And so we're going to have this NB. And that's what we're looking for. So there's our support reactions. If this were, on homework or something like that, we'd probably give you a little bit more information than I've given you here. But since we can talk through it together, we can just assume that that information was given to us. So our water pressure is, or our water surface is right here, right? It's right at the top of that gate. Now, even though we have a sloping gate, we can still calculate the pressure right here at point B, because we know that it's 2 feet below the surface of the water. And we also know that it's going to be normal to our surface. So the pressure at point B is going to be 2 feet times 62.4 pounds per cubic foot, which is the unit weight of water. And so we're going to end up with 124.8 pounds per foot. So we know our pressure at that spot because we're 2 feet deep, right? And we can, let's show that geometry over here. We know that distance right there is equal to 2 feet. We have our, I'm going to draw it right here. This is 3.11 feet. And then horizontally, we have this distance here of 2.38 feet. So we know our pressure is at what it is at 2 feet right there. And even though we're at a slope, this is still going to make a triangular pressure distribution. And so we calculate everything exactly the same way. It's just that our pressure is at an angle. And so if we can find our PB, our pressure distribution, then we can start going into W and F. And to remember, we always did these 3 steps. We go from P to W to F. And that's how we did it when it was a vertical wall. And so we'll do it the same way, even when it's a sloping gate. So that means to get W, just like before, our W, and I'll draw it right here, our W is just going to be equal to the area of the P distribution. So somebody from the front row, I'll get it started, 1/2. And then what do we multiply this by? Let's see, C and D. Alex Dresser. 1/2 times what here? I found it after.
1/2 times 124.8.
Times 124.8, yep. And then times what else? Pounds per foot.
Times 3.11.
Oh, and that's foot squared. Yeah, times 3.11. I just noticed, and I'm keeping track of all my units. I just noticed on my 124.8 pounds per foot, that should have been per foot squared. I'll write it and let me highlight it right here. That should be foot squared right there on the far right side of the screen. So yeah, W is just right the area of the triangle. So what's the height of the triangle is PB. The 3.11 is the width of the triangle. When we plug all that stuff in there, we're going to find that W is equal to 194.15. Now we're in pounds per foot. And remember, when we get these W's, this is always going to be pounds per foot into the page. So always that pounds per foot into the page. And then our next thing is we can calculate F, and F is going to be equal to W times our distance into the page. And so that's going to be 194.15 pounds per foot. Our distance into the page, they gave us over here, actually in the find statement, if the gate width is equal to 3 feet. And that's the 3 feet into the page there. And we're going to end up with F is going to be equal to 582.4 pounds per foot. Oh, thank you, Leah. Yeah, I keep on my pounds per feet. Yeah, that would just be pounds, right? That's what our for. If we look at our units here, that foot crosses out with that foot. So yeah, this is just in pounds. So 582.4 pounds. And now we can figure out the normal force at B. And we can find the normal force at B by summing moments about A equal to 0. And I think we should have all of our distances here. We know where MB is. Oh, W. Where is W? If we want to find the perpendicular distance, which wouldn't that be that distance that I'm doing in purple right there? And that would be 2/3 times 3.11 feet would be how far W is away from point A. And since we know that it's perpendicular to the gate, makes it nice and easy to just take 2/3 of that total length of the gate there. So let's see, we're going to have an NB times 2.38 feet. We'll have a minus F times 2/3 of 3.11 there. And that's everything that's causing a moment about A is equal to 0. We're going to find that the normal force at B is equal to 507.4 pounds. One question for the front row here. Why did I say that F was at 2/3 of 3.11? I showed on my drawing that that's the location for W. Is that also the location for F? How about Caleb? Degator. Am I saying that right? Caleb?
It's Degator.
Daguerre.
I don't quite remember the reasoning, but I do remember from the previous lecture that they was at the same spot as the W.
Right, it's at the same, it's at exactly the same spot. So let me add that right here. So this is, and F is also occurring at that same spot right there. And it's just, F is technically halfway into the page. It's half, that the 3 foot, our gate is 3 feet wide. So here's our yardstick, right? Our gate is this wide going into the page. Well, F is occurring right here, is occurring halfway into the page. But since we're simplifying this down to 2 dimensions, because nothing is changing in that 3rd dimension, then that gate width doesn't matter. It doesn't matter. It all looks the same to us, whether F is here or here, because we're doing a 2-dimensional representation of that right there. So that's also the location for F. So that's why I used it. That's why I could use the 2/3 of 3.11 times F. The other thing I want to point out is look how much of our force out of the total force acting on the gate, 582 pounds, look how much of that went down into the dam. The normal force at B is 507 pounds. That's the reaction from the crest onto the gate. But what about the gate onto the dam? It's the same amount. It's 507 pounds. So thinking about the stabilizing force by sloping our gate on the dam, look how big of a factor it can play. So instead of causing all this force, just, you know, causing the concrete to shear off the top of the dam, we're able to by just changing our geometry, we're able to turn that force into a benefit during those large earthquakes. Any other questions? Okay, let's look at another method. And to solve this problem. And yes, I see a question there about, is the normal force acting in the same depth horizontally as the force? Absolutely, right? It would be halfway into the page along that 3 foot width. So another method to solve this problem. Now, this method, you have to use this. The second method for curving surfaces. So we're going to get into a little bit into curving surfaces. You'll see a curving surface on your homework. And so we have to use this second method for curving surfaces. And what we're going to do, so this method breaks the pressure into vertical and horizontal components. And so this one we can use if we have a curving surface. So what we would do in this method, if we have our, let's draw our gate again. So there's our gate. We're going to have an AX and an AY. And then we would have the normal force down here at B. Instead of taking the pressure just normal to the gate, let's break it into vertical and horizontal components. And what we're going to do is we're going to figure out all the water that's sitting above the gate. So right here, this is all the water that's directly above the gate. And then so that's going to cause just the weight of that water is going to be our vertical component that's acting on the gate. Then we're also going to have the horizontal components, which is just like a pressure distribution on a vertical wall. Our we'll have a PB down here, and we'll have all of our, just a pressure distribution that's acting on that kind of like it's like an imaginary plane that our horizontal pressure distribution is acting on. So we're going to have in this, at the centroid of the area, we will have, again, we're going to have a distributed load. I'm going to call this one W1. And we'll talk about how we're going to find that. And then we are also going to have, at the centroid of the pressure, we'll have a W2. So for our vertical forces, and we will always do this approach. We'll always follow this approach. W1 is going to be equal to the area of water times gamma. So we can find the area of our water, 1/2. Let's get some dimensions back on our picture over here. This was a dimension of 2.38 feet. We had a height over here of 2 feet. So is it our dimension going to be just 2 feet times 2.38 feet? And then we multiply by 62.4 pounds per cubic foot. And this is still a W, or still a distributed load, because look at the units there. We are going to end up with pounds per foot. And so we're going to find 148.5 pounds per foot. So this is still per foot into the page. How could we convert that area into a volume? What would we have to multiply it by to get that area into a volume? Brianna, Diaz, any ideas?
The depth of the water.
Yeah, or like into the page, you mean?
Yeah.
Right. Yeah. So into the page, right? So if we took a volume of water, wouldn't that be cubic feet? And then we multiply by 62.4, and that would give us pounds, wouldn't it? Well, I do the area of water only because then it matches with our pressure stuff that we're going to do. So this is still a distributed load. We can get to the force, F1 would be equal to W1 times what Brianna said, the distance into the page. So we could find F1 by taking 148.5 pounds per foot times 3 feet. And we also know where W1 acts, because it's going to act at the centroid of the triangle here. And so wouldn't that be 2/3 times 2.38 feet? So now we know where W1 is acting. We know where F1 would act in the exact same spot. And we know what its magnitude is equal to. W2, we could find as just the same way we've done before. It would be equal to the area of the pressure distribution. And so that is going to be equal to 1/2 times PB times 2 feet. And when we plug all that in, we're going to find it's basically, let me continue it over here. W2 is going to be 1/2 times 124.8 pounds per foot squared times 2 feet. And that is going to give us 124.8 pounds per foot. And then we can find F2 would be 124.8. Write it down here, 124.8 pounds per foot times 3 feet. And so now we know where F1 is, we know where F2 is. And so F2 measured from A would be at 2/3 times 2 feet. So if we finish, we're not going to finish this problem, but if we used sum of the moments about A equal to 0 with F1 and F2, we would find that NB is equal to the 507.4 pounds again. We would find exactly the same thing. So those two methods, they give us the exact same thing. It's just a matter of, do we take the pressure normal to the gate? If I have a sloping surface, if it's a linear sloping surface, I like to do our first approach. If it is a if it's a curving surface, remember we have to use the second approach or second method. For a flat sloping surface, either will work. I like the first method better, but either one of those will work. So these two methods, one of them is pressure normal to the gate. The other one, breaking it up into vertical and horizontal components. Okay, any questions? Well, let's look at how we could apply this to a curving surface. And so let's do a problem that looks like this, and let's draw a nice big picture. Let's say we have a gate that curves down like that, and it comes in contact again. We could have a frictionless, a smooth contact down here. We can think about A as point A here as being a pin, just like our first one. And let's put our phreatic surface all the way up here. Now let's leave some room right in here to draw all of our pressure distributions. So just to the right and above the gate right here. So let's just draw on this. Let's say this is just another normal down here at point B. So point B is just a smooth contacting surface. Point A is a pin over here. And I'm gonna draw to describe our gate. Actually, and one of the reasons my coordinate system's a little bit weird. I'm gonna make y going off to the right, and I'm gonna make x going down. On your homework problem on this one, watch out for where the origin of your coordinate system is located. It doesn't give you on the picture where it's located, but based on the equation that they give you and the constant for that equation, you can figure out where the origin of that is located. Now, this is a homework problem that's not due till next week. I believe it would be due on Tuesday, but do watch out for that coordinate system on that homework problem. We're given an H here. We'll call this H1. It's equal to 10 feet. And then we have right here an H2 that's also equal to 10 feet. They tell us that this has a coordinate system, or the equation for the gate is y is equal to 1/8 x squared. And that's based on y going off to the right and x going down in our picture. And so we want to find for this problem just the total hydrostatic force per foot acting on the gate. So they don't actually tell us how far into the page it goes. It just says, hey, tell us what's the force per foot acting on the gate. This is the one where we have to stop at W. We stop at our distributed load. We don't find the force that's acting on there. And so that's why when we did the second method today, we used the area. We still found a W. We still found a distributed load. Okay, so acting on the gate, let's also add this as gate AB. And so point B is down here where NB is located. So we have this gate from A to B. Now, the reason we have to use our second approach, our second method, is because the pressure, the direction of the pressure is changing for each point. We could come to any point along our gate here. We could come to that point right there, or this point right here, or this point. And if we know the depth there, we can find the pressure. We can find the magnitude of the pressure, but it's changing direction, right? So it's changing, it's going, up at A, it's almost horizontal, and then down at B, it's almost vertical. And so the direction of the pressure is changing. Well, there are other ways to solve it. You could integrate and you could do all this other things, but really what that's going to still boil down to is breaking it up into vertical and horizontal components. So what we're going to do is we want to figure out, okay, how much water is above the gate? Well, that would be this right here. So above the gate, we have all this water right there, right? That's all of our water that's above that gate. And so we're to find those areas, let's break it up and let's say this is A1 and let's call this one over here A2. And if we can find A1 and A2, then we can find our W1, let's call it a W1, which would occur at the centroid of A1. So W1 would be about right there. The centroid of A2, I'm just kind of guessing, probably about right here, and a W2. Now we don't need to know where the centroid, where it's acting per se. We do need to figure out though the magnitude, right? Because they're just asking for the total hydrostatic force that's acting on the gate. So we have our W1 and W2, but then also remember the horizontal components. Well, the horizontal components are pressure on this imaginary surface here, this line, this vertical line at B, we technically have a pressure distribution that's triangular that starts up at the top at 0 and increases all the way to the bottom. And so we're only interested though in the pressures that it's exerted on the gate. And so we end up with a trapezoid of a PB and a PA that's acting on there. And then from that trapezoid, we can break that up into a rectangle and a triangle. And so let's call the triangle one, why don't we call that one W3? And the rectangle one, we'll call that one W4. So W1 is going to be equal to A1 times gamma. A1 is equal to 10 feet times, we need to figure out what is this dimension here. Isn't that the Y value at that point right there? And so wouldn't that be 1/8 times our X value right here? That's X equal to 10 feet based on the origin of our coordinate system being at point A. So X equals 10 feet. So 1/8 times 10 squared is 12.5 feet. So A1 is 10 times 12.5 feet. And then we can solve for W1. W2 is going to be A2 times gamma. A2 is equal to 10 feet times 12.5 feet minus the integral of 1/8 x squared dx from 0 to 10. And that's because if we take the integral, don't we find the area below the curve? So this is the integral of 1/8 x squared dx. But we want to find A2. We want to find the area above our curve there. So we take the whole rectangle and subtract out the stuff below that. So now we can find W2. Let's move on to so these are for the vertical components. How about our horizontal components? PA is going to be equal to gamma times H1. PB is going to be equal to gamma times H1 plus H2. We can find W3 is going to be equal to the area of the triangle. W4 is going to be equal to the area of the rectangle. So I'm not going into the details of those calculations, but this provides a nice template to find W1, W2, W3, and W4. Now we have one more thing. We need to find the resultant. And this is a key last step. We have W1 and a W2 going down, and we have a W3 and a W4 going to the right. Our WR is the hypotenuse of that triangle. So WR is equal to the square root of W1 plus W2 quantity squared. So we have to add up the horizontal components and square them, and then W3 plus W4, add up the horizontal components and vertical components. Then we can find that WR term. So don't forget, draw this last picture.